Hello, Suresh. Is my voice audible?
Yeah, audible, sir.
We will wait for 2 more minutes and then we will start. Let the few participants join.
Okay, sir.
Yeah. Welcome to the. So, is the screen visible to you?
Yeah, visible, sir.
Yeah. So, in the previous class, we have seen regarding the delays with respect to the gates. So, now let us see how you can write the programming to the with respect to the data flow modeling.
Sir,
Hello.
sir, can you please briefly explain the yesterday's class, sir?
Which one? So yes.
Brief one, sir, because there is a gap between the yesterday, sir. Maybe the other person has taken class.
Yeah, that is totally different from the gate level modeling and the actual and the data flow modeling. Okay, so no issue about that. So it is a different thing. Okay, so there will be no link. Okay, so the next one is data flow modeling. So how you can write the programming in Verilog using the data flow modeling. Okay, so the gate level designs. So the gate level design description. So make use of the gate primitives. So we have seen that. So whatever the gate level description we have done in the previous classes. So in this we have used the gate primitives. Okay. So by using these gate primitives, so we have designed the we have written the program in the Verilog. Okay. So if whatever the programs we have done, these are smaller programs. So if we are going for the bigger program, means we have to take many gates. Okay. So we have to take many gates and repeatedly we have to instantiate the gates in order to achieve the full design description. Okay. So but whenever whenever the number of gates are too high, means also automatically the design description will be a little bit problematic. Why? Because so if the number of gates are more, so it will be quite complications in terms of the connections also. Okay. So in order to overcome that, so we are going for the next level of design hierarchy. The next level of design hierarchy is the data flow level. Okay, that is the data flow level description of a digital circuit is at a higher level. So it makes the circuit description more compact when compared with the design through the gate level or design through the gate primitives. Here we use a number of operands and operations representing the simulations directly or indirectly, and the more important one is that the operations are carried out on the operands. Okay, so these operands can be done in the single operation, or we can go for the multiple operations. The results, whatever the results we are getting here in the data flow, so the results are assigned to the nets. Okay, so the results are assigned to the nets here. So the operand operation assignments representing the data flow are carried out repeatedly in order to complete the design description. So now let us see the main thing here. So whenever we want to write the program in Verilog program in the data flow modeling, so we have to write the equations. So sorry, we have to write the expressions, so which are nothing but the continuous assignment expression. So or you can call it as continuous assignment structures. Okay, so here we have to assign the output of a circuit to the operations, so to the various operations. So that assignment is called as continuous assignment structure or continuous assignment expression. Okay, so for example, let us take a small thing. So let us take a 2-input target here. So let us take a 2-input target. So this gate has 2 inputs A, B, and it has an output Y here. Okay, so in order to assign these in terms of data flow, so we can assign in the following format. So that is assign Y is equal to A or B. Okay, so it is the R symbol. Okay, if it is AND gate means, so it is A and B. If it is XOR means, you can write A XOR B like that. So these operations, so these operations we have seen in the previous classes, the symbols of various operations. So we have seen in the previous class. Okay, so we have to assign like this: assign Y is equal to A or B. Okay, here assign is a keyword. Here assign is a keyword, so that is used for carrying out the assignment operation. So in order to assign the output with the required operations with respect to the input operand, so assign keyword is used. Okay, so this keyword is used in order to carry out the assignment operation. Okay, so this type of assignment is called as continuous assignment. Okay, so whenever we are writing the data flow, so we have to write the assignment equation, so which is known as the continuous assignment. The statements which are used in the data flow, they are called as continuous assignment statement. Okay, so remember that the statements which you are writing in the data flow model, so they are referred to as continuous assignment statements. So how these continuous assignment statements are declared means, so they are declared by using a keyword known as assign here. Okay, so from the assign Y is equal to A or B, so assign is the keyword and A and B are the operands. So here A and B are the operands and R is the logic operator here. Okay, so equal to is an assignment activity. So it is an assignment activity to be carried out. Okay, where here y is a net. Okay, so it is a net representing the signal to which the operation of this operand should be assigned. Okay, so that means we have to describe the output as a net. So it is the thing you have to keep in mind. So whenever you are assigning something to a variable, that variable must be declared as the net. So that means it may be a while or try. So that we have to remember. So now in general, so if you take in general, the operand what you are giving, so that is the operand means A and B. The operands what you are using in the data flow modeling, so they can be a constant numbers. So operands can be constant numbers. So can be constant numbers. So next, they can be a scalar, a net, which is a scalar, or a vector. Okay, so it can be a net which is a scalar or a vector, and the operand can be a registers. The operand can be a registers. So this register may store a scalar value or a vector value. So scalar means single bit and vector means a group of multiple bits, and so it can be a function. The operand can be also a function. Okay, so these are the various things the operands can be assigned. Okay, so whatever the thing you are doing here, so that should be used by using the assignment statement. So let us write a small program here. So this small program, let it be for AND gate here. So how to write a program for AND gate in the data flow? Okay, so first module data flow, and okay, so for an AND gate, so take the AND gate here. The inputs of this AND gate are AB and output is Y. Okay, therefore I am assigning the outputs and inputs Y comma AB and output C. So the inputs here are AB. So that is input A comma B. So after that, so when you are assigning the output, we have to make sure that the assignment which you are using after the operation of the operands should be a net. So that means whatever the inputs here, so these inputs in the data flow will be taken as the operands. Okay, so on the operands, the operation will be carried out, and that the result of that operation should be assigned to a net. So that will be assigned to output normally. Okay, since the operation should be assigned to a net, so therefore the output here should be assigned to while. Okay, while. So now use the continuous assignment statement. Assign y is equal to a and b. Okay, so assign y is equal to a and b and end module. So this is how you can write a AND program in the data flow here. So just so by using the continuous assignment statement, assign y is equal to a and b. So here what you are doing, so if you are using the continuous assignment statement, so that y should be declared as a net. Okay, since I am going for the single assignment, so that is I am going for the net that is carrying a that is driving by a single data. So we are using it as while y. Okay, so this is how you can write the program for your AND gate. So now let us see how you can write a program for the AOI gate. So let us take an AOI gate here. So AND gate. So A and invert and NOT gate. So it is an AOI gate. So with the inputs A, B, C, D. Okay. So here we have the output Y. So for this AOI gate, I have to write the program in the data flow modeling. Okay. So in order to write the program in the data flow modeling, here what you can see is that Here there are whites itself in the programming. So what are that whites? So here there is a white that is connecting from the, so before that let us label the gates G1, G2, G3 and G4. So labeling of gates can also be done here for our perception. Okay. So there is a wire that is connecting from the G1 to G3. So let that wire as W1. And also there is a wire that is connecting G2 and G3. Let it W2. And also there is a wire that is connecting G3 and G4. So let it be W3. So here there are 3 wires here. Okay. So this to be represented. So this has to be represented in the form of whites. Okay. So when you are writing the program here, the first thing is module AOI gate. So output is Y and the inputs are A, B, C, D. Okay. So next specify the inputs and outputs here. So input A, comma B, comma C, comma D, and the output is taken as output Y. Okay. So next here we have to declare the whites. So which are connecting the 2 components. So let the whites as W1, comma W2, comma W3. Also, when you are writing the program in terms of data flow, so declare the output also in terms of net. So which is a Y here. So Y. So now after that you can go for the assignment. So first assign W1 is equal to. So what is W1 here? W1 is equal to A and B. So bitwise and operation I am taking. Okay. So after that, in order to get W2 here, so assign W2 is equal to it is C and D. Okay. So next I have to get W3 here. So R operation. So output of this OR operation is W3. So the inputs of this OR gate is W1 or W2. Okay. So next assigned Y. Next we have to go for NOT gate here. Output of NOT gate is Y here and the input of NOT gate is W2. That is NOT of W3. So and end module. Okay. So this is the program how you can write in the data flow. Okay. So there is one more method here. So how you can assign the things here. Okay. So instead of using the multiple assignment statements, so you can use the single assignment state. Why? Because so all these outputs are of single bit, that is the scalar value. You can use the single assignment here. So what you can do is assign W1 is equal to, the first one is A and B, comma W2 is equal to C and D, comma W3 is equal to W1 or W2, comma Y is equal to not W3. So we can assign them in a single line. So this is the one of the way how you can assign them, or else you can assign them in the by using the multiple assignment statement. That is by using the multiple continuous assignment statements. So we can use the single assignment statement, or you can use the multiple continuous statements here. So here the semicolon terminates. So whenever you are using the semicolon, means the semicolon terminates the continuous assignment statement. Okay. But whereas comma here, so these comma separate the different assignment statements in the given continuous assignment statement. This we have to remember. If we are using comma, means so we can use the multiple statements under the same assign keyword. So if you are using the semicolon, means the assignment statement will be ended. So that is the assignment statement will be terminated, and whatever the things we are using on the LHS, so that will be W1, W2, W3 and Y. All these should be declared as a net type. So all these should be declared as a net type. That is either a while or right, as we defined. So depending upon that, we have to define them. So they must be, all the LHS operands should LHS assignment should be of net type. That we have to remember. Okay. And moreover, all the operands in an assignment are evaluated. So whenever there is a change in the value of the assignment statement, and moreover all the assignments which you are made. So that is all the assignments which you are made. So these are concurrent statements. So these are carried out concurrently. That means all the statements will be executed at the same time. Okay. So hence the order of the statements is immaterial. Okay. So normally when you are going for the some of the computer programming languages, so the lines will be executed step by step. That is, first the line 1 will be executed. So based on the result of the after executing line 1, so line 2 will be executed. After executing that, line 3 will be executed like this. But in case of Verilog, so it is a concurrent language, and moreover, so all the statements in the data flow statements will be executed concurrently. So that means there is no need to write in the order. So the order of the assignments is immaterial. So you can use any order. So you can assign this W2 at the top, and you can use this W1 at the bottom, like this. So you can use Y here at the second place. So anything you can use. So it is immaterial. And moreover, so whatever the assignments you are using on the RHS, okay, the assignments which you are using in RHS can be a nets or registers or a functions. Okay, so that means here A, B, C, D can be a nets or registers. So this is how you can write the programming in the data flow modeling. So next, let us go for a concept known as combining assignments and net declarations. Okay, so combining assignments and net declarations. Yeah. So if you see the above program here, so what you have written the above program here, you have declared while, okay, you have declared wire W1, wire W2, wire W3, and wire Y. Okay, so after that, you have assigned a W1, W2, W3. So for sometimes what you feel is that I am declaring the output as a wire, and also I am declaring the thing that is connecting two components as a wire. So if you get confused with that, so there is a concept in the Verilog in the data flow, so that we can combining the assignments as well as the net declaration. So for example, you can take the same AOI gate. Okay, take the same AOI gate example, so which we have seen so far. Okay, so A, B, C, D, and Y as the outputs. So in the previous case, what we have done? So first, so it is W1, W2, W3. So what we have done here? So first, after declaring the inputs, so module AOI data flow, so output Y A, B, C, D. So after that, so what we have done, we have declared the inputs and outputs separately. Input A, B, C, D, and also output is Y there. So after that, so I have declared Y, W1, W2, W3, and anyway the output should be net. So I have declared that as Y. So after that, I have used the assignment statements which you have seen. Okay, but what you can do is that, so in order to overcome the number of white declarations, so what you can do is that, so you can directly declare the output Y. So this should be must. Why? Because anyway the output, so whatever the thing we are using, so that output must be should be a net. So therefore Y. Okay, so Y. Next, after that, so next W1. So W1 is the output of and AB. Okay, so it is also a wire here. If you see, the W1 is wire. So instead of defining separately the wire and assigning statements, so what you can do is that wire W1 is equal to, so wire W1 is equal to A and B. Okay, so after that, wire W2 is equal to C and D, where W3 is equal to W1 or W2. Okay. So here what we have done, so I have not defined W1, W2, W3 separately. So in the previous program, if you see what I have done, so I have defined W1, W2, W3 separately. After that, by using the continuous statement, I have assigned them. Okay. So the other way is that, so directly we can assign. So where W1 is equal to A and B. So instead of declaring the white separately and assignment, so directly I can assign where W1 is equal to A and B, where W2 is equal to C and C, where W3 is equal to W1 or W2. So after that, after assigning that, that is, you must remember that, so these while and assignment combining declaration should be done only for the nets that connecting two different components, but the final output which is declared as white should be done by using the assignment only. So assign y is equal to, so how you are assigning y is equal to not of W3. So y is equal to not of W3 end module. So that is end module. So this is how you can combine the assignments as well as the net declarations. Okay. So this is the way how you can combine assignments as well as the net declarations. So you must see this. So this is very important concept. Okay. So when you are coming about writing the test bench, even though we are writing the different modeling, but the test bench is the same. So let us write a test bench for this. So if you are writing the test bench for this, so module test bench. So I have taken the module name as test bench, and you should remember that when you are writing the program in the data flow modeling, sorry, for the test bench, so no need to write the port list. Okay, so after that you have to declare the inputs as registers. So here in the inputs for this program are A, B, C, D, and the output should be declared as y. So y. Next, we have to instantiate the module for which we are writing the test bench. So I am writing the test bench for the module that is AOIDF. So instantiate AOIDF. So it is label name of that module is Z1. You can take any label name and write the list of port names Y, A, B, A, B, C, D. It should be the same list of port names here. So after that, we have to assign the input values. So in order to assign the input values, so in the previous class we have seen that here we can use the initial block or always group. Okay. So I am using the initial block. So initial begin. Let us take dash 0. So at 0 instance of time, so A is equal to 0, B is equal to 0, C is equal to 0, D is equal to 0. So after 2 units of time, assign A is equal to 0, B is equal to 0, C is equal to 0, D is equal to 1. So again after 2 instance of time, so assign A is equal to 0, B is equal to 0, C is equal to 1, and D is equal to 0. So like this, you can assign all the input combinations. Okay, so since there are 4 inputs here, we have the input combinations from 0 to 15. Okay, so from 0 to 15, apply all the combinations here. So after assigning all the combinations here, so next we have to end the initial statement. Okay, so after that we have to use the, if you want to plot the time. Okay, so if you want to print the output with respect to time, you can use the monitor statement, that is initial $monitor. Okay, so $time. So this $time will print the simulation time. So $time. A is equal to percentile B. Why? Because since these are the binary numbers, I have used percentile B. B is equal to percentile B. C is equal to percentile B. D is equal to percentile B. So after that, so output also we have to give it. So y is equal to percentile b. So this order is immaterial. So we can use any of this order. Okay. So but when you are specifying this, so this order will be mattered. Okay. So if you are specifying a comma b comma c comma d comma y means, so the outputs will be plotted in this manner only. Okay. So a b c d y. Okay. So whatever there in the quotations here, so that will be printed as it is. So the first percentile b, okay, so will be assigned to a. Second percentile b will be assigned to b. Third percentile b will be assigned to the c here. So fourth one will be assigned to d, and the y will be assigned. Last one will be assigned to y. So the assignment will be taken from the left to right here. Okay. So after this, next we have to give the simulation time. Okay. So in order to give the simulation time, so give the command here initial dollar stop or dollar finish. So as 100. So I'm simulating it for 100 time units. Okay. So after that end module. So end module is the thing here. So that is I am my simulation will stop at 100 time units. Okay. So this is how you can write the test bench program for this. Okay. So this test bench program will not be changed for the anything you write. That is for any modeling you write. Okay. So the next. So after this, next we will look at the continuous assignments and strengths. So far we have seen the strengths in the gate level modeling. Okay. So whenever we are getting the same input value to a particular node, so we are going to solve that depending upon the strength here. So the concept of strength is also applied to the data flow modeling. Okay. So as seen in the gate level, so here also we have the four strengths relating to the logic here. That is the logic gates. The first one will be the supply. So the next one will be the strong. Next one will be the pull, and next one will be the weak. So these are the four supply voltage. These are the four strengths related to the logic. Okay. So that is the logic values. And regarding the capacitance value, we have the large, small, medium, and small. Okay. So whenever we are using the continuous assignment statement, whenever we are using the continuous assignment statement and you are using the strength means, so let us see how you can assign them. Okay. So wire pull 1 comma strong 0 y is equal to not y1. So this is the thing how you can assign here. Okay. So here assignment y. Okay. So the assignment y is compared with the assignment y is combined with the wire declaration into a single statement. Okay. So this is the one way. The another way is that what you can do is you can define y separately. So you can define y separately. After declaring the y, so you can use like this. So assign pull 1 comma strong 0 y is equal to not of y1. So this is the one more way how you can assign. So when you are using the assignment and combinedly, this is the way. And if you are using the assignment and y separately, this is the way how you can combine it. Okay. So now let us see a small example here. So how you can use the statements here. Okay. Let us see a small thing here. So for example here, so before that, yeah. So take a NOT gate here. and also a NOT gate here. So take two NOT gates, A, B. So the output is Y here. Okay. So now write the program for this module. So module strength in data flow, output is Y and the inputs are A comma B. Okay. So here both the output nodes of these inverters are connected to only one output node, that is Y. Okay. So now declare the output as output Y. So and declare the inputs A comma B here. Okay. So now here we have to declare. So we have to declare the output as a net in case of the data flow modeling. So declare the output as Y. So Y Y. So now assign uh, strong 1 comma, so assign strong 1 comma pull 0. So assign strong Y comma pull 0, or else what you can do is that simply, okay, so Y is equal to, not A. Okay. So in the other case, assign pull 1 comma strong 0 Y is equal to not B and end module. So here for this NOT gate, so I have used the strengths as strong 1 and pull 0. For this NOT gate, I have used the pull 1 and strong 0 as the strength. So now if you take the truth table, so A, B and output Y. So if we are giving the two inputs as 0, 0, okay. So 0, 0, since we are giving the same input here. So the output of the two nodes will be 0, 0. So therefore there will be no problem. So if I am giving the two inputs as 1, 1, so sorry, here 1. So the output here will be 1, 1. Sorry, 0, 0. If you are giving 1 means it is 0, 0. So since the output is 0, 0 here, it will be no problem. Output will be 0 will be assigned. But when you give A is equal to 1 and B is equal to 0. So when you give A is equal to 1 and B is equal to 0 here, so the output of first NOT gate will be 0 here. So here the output of second NOT gate will be 1. So that means to that particular node Y here, so we are assigning two different logic values. So we are assigning two different logic values, that is 0 and 1. Okay. So now in order to overcome that, here we have to go for the strength here. Okay. So for this gate here, so for the first gate, so what is the output is 0. So here the logic is 0. So that is, since it is giving the output 0, its corresponding strength is pull. Okay. And for the second gate here, the output is 1. Okay. So therefore output is 1 here. So that is the corresponding strength for this one is second gate, that is 1, it is pull. So again it is having the same strength. Okay. Since it is having the same strength, here we get the undefined value. Okay. So next, give A is equal to 0 and give B equal to 1. So now give A equal to 0 and give B equal to 1. So therefore the output of first NOT gate here will be 1 and the output of second NOT gate will be 0. Okay. So again we are assigning the different values to output Y. So now again we have to go for the signal contention here. Okay. So that is the strength checking here. So for the NOT gate, the output is 1. That is the logic 1. So therefore, for first NOT gate here, output is 1. So whose strength is strong? Similarly, for the second NOT gate, the output is 0. So 0 means 0 corresponding strength we have given is strong. So again, the two strengths are same. Again, here we are getting the contention resolution here. So that means here we cannot solve the output even though we have assigned the strength. Okay. So therefore here we have to go for the declaration of the things which I have told you. So that is, we have to go for the declaration of in order to assign that. So here we have to go for the declaration of that is wire and so WAND var, we have to go for the declaration. So in order to here, so you can declare the output again in terms of WAND y. So WAND y means what it does is that, so y is equal to a and b. So 0, 1 and 0. So output is 0. Here 0 and 0 will be assigned if you are declaring the WAND. And if you are declaring the var here, if you declare var means, so R logic. So that is 0, 1, R logic is 0. So therefore, sorry, 0, 1, R logic is 1. So therefore here 1 will be assigned if you are using the var. Okay. So or else, now let us see here. It is strong 1. So instead here go for weak. Here go for pull here. Okay. So now see here. So A is equal to 0 and B is equal to 1. So A is equal to 0, B is equal to 1. The output of first NOT gate is 1. So output of second NOT gate is 0. So now check for the strength. So for the first NOT gate, the output is 1, whose strength is strong. For the second NOT gate, the output is 0, whose output is 0, whose strength is full. Okay. So if there are two strengths, okay. So now if you compare the strengths, so what is the order of strengths? The first one will be supply, second one will be strong, third order of the strength is full, and next one is weak. Okay. So for the first, that is for the logic one, we have having the strength. For the second gate at present, we are having the strength as full. So among the strong and full, which one is stronger? Strong is stronger. So therefore logic 1 prevails. So strong is applied to logic 1. So therefore logic 1 will be the output. Okay. Next, when you apply 1 0, so when you apply 1 0 here, so the output of the first NOT gate is 0. So the output of second NOT gate is 1. Okay. So therefore again here we have to go for the strength checking here. So for the first gate, we are getting the output as logic 0. So therefore the corresponding strength is full. For the second logic, we are getting the output as 1. So that is the strength for the second gate here. For the logic 1, the strength is weak here. Okay. So therefore when you compare full and weak, so in full and weak, which is having the strongest strength here? Okay, full is stronger than weak. So therefore full, the logic which is connected to full will be revealing. So that means, so full, that is 0 here. So therefore the output will be 0. So like this we can assign the strength contention in the data flow also, and we can able to solve the output values. Okay, so this how you can write the programming here. So next, similarly we have the delays. So we have the delays in the data flow also. So let us see that. So the delays and continuous assignment. In case of data flow, we have seen the delays with respect to the net and with respect to the gate, and also the tri-state gate delays. Okay. So similarly, the delays also can be incorporated at the data flow level in different ways. Okay. So consider a few of the combinational circuits which you have seen previously here, or else take y is equal to sorry, or else what you can do is, so y comma a comma b. Okay, so y comma a comma b. So now assign here, assign hash 3 y is equal to a and b. So if you see these structures here, what happens is that the assignment here, so the assignment takes the effect with the delay of 3 time units. Okay, whenever, so when here what we have taken, y is assigned with the AND gate. Okay, so y is assigned with the AND gate here. Okay, so whenever there is a change in the value of a or b, the program waits for 3 units of time. Okay, so it waits for 3 time steps, then it will compute the value of y. Okay, so compute the value of y based on the inputs a and b at the time of computation, and assigns this value to c here. Okay, in mean period, in the same time, if a and b are further changed, so in the same time if a and b are further changed, it means the c, but the output y will also change and takes the new value only after 3 units of time, after the 3 units of time, with respect to the changes in the a and b. So now let us see a small example here. So first take 2 inputs. So take 2 inputs here. So first draw the time slot. So 0, 3, 6, 9, 12, 15. So these are the different time units I have taken, time steps. So first take a here. So initially a is 0. After 3 units of time, the value of a becomes 1. Okay. So similarly, b also is initially 0. So after 3 units of time, the value of b goes to 1. Okay. So therefore, if you take the output y here, so if you take the output y, so initially the output value, since I am going for the things here. Okay. So at 0 time units, so at 0 time units, what happens at 0 time units, this value, that is a and b is 0, means the output y should be 0. So AND gate a 0 b 0, so AND operation of a and b should be 0, but this value will not be assigned to y immediately. The value of y will be assigned to y, so only after the delay specified here. So I have specified the delay of 3 time units. So that means at 3 time units, the value of y will be 0. The value of y will be 0 here. So at this point of time here, it is undefined. The output is undefined from 0 to 3 time units. Why? Because even though I have assigned the input values a and b at 0 instance of time, since I have used the #3, that is the delay is 3 time units, so the output will be assigned only after 3 time steps here. So now let's come here. Okay, so I have assigned the delay. So whenever the simulator simulates at a and at 3 time units, what happened again? At 3 time units, the value of a is assigned to 1 and the value of b is assigned to 1. Okay, so the assignment operation will be carried out. At least one of the operand will change its value. Okay, so here both the values are changed here, so automatically the output changes. So at 3 units of time, what happens? A is equal to 1 and b is equal to 1. So at a is equal to 1 and b is equal to 1. So that therefore the output y is equal to 1. Okay, this output y will be instantiated only after 3 units of time here. So that is at 6 units of time, the output y becomes 1. So now, for example, at 5 units of time here. Okay, so at 5 units of time, what happens here? So 5 units of time here. So the value of a is changed to 0. So the value of a is changed to 0 here. So the value of 5, if b a is changed at 5 time units, the value of b will be the same. Okay, so now even though here we have changed the value, okay, so here the output value will not be changed instantly. So at 5 units, what is the value? At 5 units, A is equal to 0 and B is equal to 1. So what will be the output? Y should be 0. Okay. So delay of 3 time units. That means only after 8. That is, the change is happening at 5 time units and the delay is 3 time units. So therefore, the time at which the output Y will be changed is at the 8 units of time. So at 8 units of time, again the output Y becomes 0. Okay. So like this, you can use the delays in case of the data flow programming here. So like this, we can use the delays in case of the data flow program. So there is one more way of assigning the things here. Okay. So instead of using the assignment statement, if there are multiple wires, means what you can do is that, so you can directly use like this: wire A comma B comma C if you declare means, so or else wire A comma B. Okay, so you can directly declare like this: wire C is equal to or sorry, delay of 4 time units, so C is equal to A and B. So it is one more way of assigning the delays in the data flow. So this is way how you can go for the assignment of data flows here. Okay. So the next important one is, which we have seen previously, the concatenation operator here. So the continuous assignment statements, we can assign on the RHS side, we can assign the vectors as well as we can assign the scalars. Okay. Now when you are going for the when you are going for the assignment of anything, that is by using the operation, sometimes what happens is that, suppose if you are going for the addition, okay, so if you want to add 2 bits, so A and B are the 2 numbers, if you want to add 2 bits, so for example, what happens is that when you are add 2 bits, that is 1 and 1, okay, so you get the output as sum output and carry output. Okay, but when you are declaring it in the data flow, for example, if C is equal to A plus B, we are declaring. So C is equal to A plus B means I am adding the 2 numbers here, that is A and B. So, but the output here we are getting the 2 bits. Okay, so we are getting 2 bits. So I have declared the input as also as single bit. So, but I cannot assign 1 0 to C here. Why? Because it is a sum and it is carry. Okay, it is sum and it is carry here. So therefore, I cannot assign C is equal to A plus B directly. So it is the different thing here. Okay. So therefore, what I can do is that, so if it is a normal addition means I can add. But sometimes if I am going for the binary addition means, so this type of thing, it is not possible. Okay, so I have to go for the use of concatenation operator. So let us see how you can go for the use of concatenation operation here. Okay, so for example, I want to add 2 numbers A and B. Okay, so I want to add 2 numbers A and B here. So A is of 4 bits, that is 3 down to 0, and B is of 4 bits, 3 down to 0. So therefore, the bits are A3, A2, A1, A0, and the bits are B3, B2, B1, B0. So if we add these 2 numbers, so what I am getting here, I get a S0, which is the sum. So after getting the sum here, so I get a carry, so which is some C0 here also, or else you take the input carry here, CCI. So input, or else you take it as IC, that is the input carry. So you get C0 here, again the sum is S1, again you get a carry here, which is forwarded to next stage. So take it as C1, so you get sum S2 here, you get one more carry C2 here, so sum here, and finally you get the output carry. So now you need to show what are the sum output and what is the sum output, and you need to show what is the carry output separately. So in order to do that, so what you should do is that, Here you can write the program by using the concatenation operator. Module add 4-bit. So what is the output carry? Output carry is, let it take as C0. Okay, output carry, let it, you take it as C0. So after that, next what you can do is that you take the output sum as yes. Okay, so after that you take the input as A and B. Okay, so these are the this is the output, and there is one more input here, so which is known as the carry in. Okay, so now declare inputs and outputs separately. So input carry is a single bit, so therefore it is a scalar, so therefore define it separately. So after that, so A and B are 3 down to 0, it is a 4-bit. So A input 3 down to 0, A comma B, that means A and B are 4-bit data here. So after that, so after defining the input bits, the next one is we have to define the output. So output 3 down to 0, yes. So output 3 down to 0, yes. So after that, there is one more scalar output, that is out C0, out C0. Okay. So next here, we have to use the concatenation operator in order to combine both of these. Okay. So now declare the output, that is C0 and output as whites here. So white 3 down to 0, yes, as well as white C0. Okay. So next after that we have to assign this. So how you can assign means, so assign. So now after adding this, the last one we are getting it as C0. Okay. So if we add this last 4 bits here, so the last thing which you will be getting is C0. The remaining will be S3 to S0. So therefore use the concatenation operator. So the first will be C0. So whatever the last bit you get at the MSB, which is nothing but C0, and the next one is some output which is S. So which is equal to. So we are adding this. How you are adding? We are adding input A plus input B plus C. Okay. So there and end module. So it is equivalent to the ripple carry adder. So if you are writing the ripple carry adder program in the data flow, so it is this much simple when you compare with the gate level modeling. So when you are writing the program in the gate level modeling, so it is very difficult. So but when you are writing the program in the data flow, see how simple it is here. Okay. So now let us see how an ALU program here. So how you can write a ALU program using the data flow modeling. Okay. So I want to design an ALU. Okay. So ALU has 2 inputs here. So ALU has 2 inputs. So what are the 2 inputs means? A, B, and also it is having one more input which is C in. Okay. So basically, I want to do the operation of the first operation I want to do is addition. I want to do the subtraction. I want to go for the, after doing the subtraction here, I want to go for the XOR operation here, and also I want to go for the bitwise AND operation. So bitwise XOR operation and bitwise AND operation I want to perform. Okay. So these are the 2 arithmetic operators and 2 logical operators I have to perform by using this ALU. So therefore, it is a 4-bit ALU. So that means the operands here will be the 4-bit operands. So therefore, A is having 4-bit width. So 3 down to 0, 3 down to 0, Cn. Okay. So the output here. Okay. So the output here will be what I can take is that. So take the output as Y and output as C0. So if you add A and B, so you get carry out, that is C0, and also if you do the subtraction, if there is any borrow here, that will be final borrow, means it is C naught, which will not be there actually. So for the sum itself only I have taken C naught. So sorry, for the carry itself I have taken C naught. Y is also 3 down to 0 here. So which is nothing but the sum. Okay, so now how I can write the program here. Okay, the first one is module ALU data flow. So output is Y comma C naught comma A comma B comma C in. Y comma C naught comma A comma B comma C in. After that specifies the output and input separately. So output 3 down to 0 Y. So after that specify output C naught. Later specify the input. So input 3 down to 0 A comma B. Why? Because both A and B are of 4-bit data, and input C in. So I have specified it. Okay. So after specifying it, the next thing what we have to do, so we have to declare the outputs in terms of whites here. Okay, so declare the outputs in terms of white. White 3 down to 0 Y. While C naught. So when you are writing the program in the data flow, that is in the continuous assignment statement, the output will be declared as next. Okay. So first, here when you are writing the ALU program, here we have to do 4 operations. Okay. So now we cannot do all the 4 operations at the same time. So now in order to do the 4 operations, let's take 2 selection lines here. Okay, so that 2 selection lines will be S1 and S0. Okay, so take the 2 selection lines S1 and S0 here. Okay, for example, if S is equal to, that is selection line S1 comma S0 is, or simply I can take it as S. Okay, so if S is equal to 0 0, I have to perform the addition operation. If S is equal to 0 1, I have to perform subtraction operation. If S is equal to 1 0, I have to perform the XOR operation. If S is equal to 1 1, I have to perform the AND operation. So here, if S is equal to 0 means addition, S is equal to 1 means subtraction, S is equal to 2 means XOR, S is equal to 3 means AND again. So why? So that means the S value should be a 2-bit data. So why I am selecting the 2-bit data for a selection line means, so I have to perform the 4 operations. If the number of operations increases, so I can increase the data size of my selection line. Okay. So now this selection line is also a input. Okay. So therefore input. So based on this selection line only, we are able to solve the select the choice of the output. So 1 down to 0. So it is a 2-bit data. 1 down to 0. Yes. Okay. Now assign here. Okay. Concatenation. Use the concatenation operator. C naught comma Y is equal to C naught comma Y is equal to the first condition. Okay. The first condition is, if the condition is, if S is equal to 0 0, we have to go for addition. Otherwise, we have to go for the next. Okay. So in the data flow, we have a conditional operator. So which is conditional operator, which is question mark semicolon. If the condition is true here, so the true statement will be executed. Otherwise, the false statement will be executed. Okay. So first, what I do is that by using the conditional operator, I write the program. Okay. So initially S is equal to, the condition is S is equal to 2-B00. So that means if the 2-B means, so S is a 2-bit data and we are assigning the value of 00 to it. Okay. So if it is 00 question mark. Okay. If S is equal to 00 means what we have to perform? We have to perform the AND operation. So therefore, it is the true statement, A plus B plus C in. So this statement will be performed. Okay. So otherwise we have to go for the next. So that means now we have to check whether the selection line is 0, 1 or 1, 0 or 1, 1. So therefore, I am using the nesting of the conditional statements. So instead of going for the false directly, in the false statement, what I do again, I use a statement here, that is if S is equal to 2B 0, 1. So now in the, so if S is equal to 0, 0 means this condition will be executed. If it is false means it comes here. So in the false, I am using the nested conditional operator here. It will check S is equal to 2 dash B 0, 1. If it is the condition is true here, subtraction operation will be done. That is A minus B will be done. Okay. So after that, again I have to go for the, there were two more conditions. So therefore I am going for the third condition. Okay. If S is equal to 2B dash 1, 0, if it is true means I have to do the XOR operation, that is A XOR B. Okay. So I have checked the first three conditions. Okay. If the first three conditions are not done, the last one will be the automatically correct. So therefore, no need to use the condition for the last one. So therefore, directly use A and B. Okay. So now close all the conditions here and use the end module. So this is the program how I can write for the ALU program when I am using the data flow modeling. So this is the program how I can write here. So this is for the day here. So I hand over to Suresh.
Hello.
Suresh.
Yeah, okay, sir. Yeah, thank you, sir.
Okay.
If you have any queries, please ask this, sir. Otherwise, now we closing this session. Yeah, if you want repeat the, if you want to see the this videos, I will share the my YouTube link. Okay. Okay. Thank you, sir.
Okay. Thank you, Suresh. Thank you, one and all.
Yeah, now session is completed. And I sign out this session. Please leave the session. Thank you.